Hello everyone, this is Dr. Young, and in this video we're going to continue our conversation on measurements of concentration. In previous videos we talked about the percentages. This one we're going to focus on molarity. So before we were talking about, it's important to be able to measure concentration because you want to know how much stuff is in solution. You want to know how much of a solute there is or how many molecules of a solute that there are in a solution. There are many different ways to measure concentration. In the first video we talked about percent by mass, percent by volume. We're not going to talk about ppms or ppbs. And in this video, we're going to talk a lot about molarity and how important molarity is and how we do math with molarity. These are not the only measurements of concentration. There's also molality, for example. There's osmolality. There's equivalence. There's all kinds of different ways that you can measure concentration. But for us, molarity is going to be key. Molarity is one of the most important. In my opinion, it's going to be the one that you see the most. It's the most important measurement of concentration. And I'll explain why here in a second. Most important measurement of concentration. So let's take a look at this example down here, right? So let's just say hypothetically, you've got two solutions. We've got 100 milliliters of whatever solvent. So say we've got 100 milliliters of a solvent in both of these, right? So these are both 100 mils. And in one of these, right, you're going to take your triphenylphosphine and you're going to put 34 grams of triphenylphosphine into 100 milliliters of solution, right? So if you do that, right, if you put 34 grams into 100 milliliters, that's what we were talking about before, right? One way to talk about that concentration is to just do the percent by mass. So in this case, this would be a 34%, right, mass by volume solution, 34%. Now if I took 34 grams of ammonia instead, so I'll take 34 grams of ammonia and add that to my solution. It doesn't really matter that it's ammonia or anything, it's just the fact that it's 34 grams means that this is a 34% solution. All right, so this would also be a 34% by mass solution. So with that measurement of concentration, right, it looks like these are both 34%, and so it looks like they kind of have the same concentration, right, the same measurement of concentration. But what I want to make the point I want to make, and which is the whole reason why we're talking about this video and the whole reason why we have molarity, is that these, in fact, are not really equal concentrations, right? They don't have the same amount of stuff. In chemistry, we care about how many particles there are, how many ions, how many molecules, etc., are dissolved in solution, because that's going to be really important when we talk about reactions, when we talk about osmosis, when we talk about pH, and I'll write all this on the next slide here. So what I want you to look at here, right, so if you actually consider this, I wrote the molar masses here also. So for the for phosphine here, I've got 34 grams of phosphine, right? But if I want to know how many phosphine molecules there are, I need to look at the molar mass to figure out how many moles there are. So this looks like it weighs about 34 grams per mole, or in other words, this is 1 mole of phosphine. So if I added 34 grams of phosphine, that would be 1 mole. And I'll just represent that as, I'll just draw 3 phosphine molecules to kind of represent the equivalent of 1 mole, right? So I've got a certain number of phosphine molecules. Now, if I do the same exercise over here with ammonia, ammonia doesn't weigh 34 grams. It only weighs 17 grams per mole. So if I'm adding 34 grams of ammonia, now I'm actually adding 2 moles of ammonia. So I'm actually adding twice as many ammonia molecules as I am phosphine molecules if I add 34 grams of each. And so I'm going to draw that as just literally twice as many. So over there I drew 3 phosphines. Here I'm going to draw 6 ammonias. That's kind of a weird end, but we're going to go with it. We're going to draw six ammonias here to represent that there are twice as many molecules in here, right? So if I look at this, this has twice as many molecules. Right, it has twice as many molecules as the one on the left. And that's going to be really important because that means that this one over here is actually twice as concentrated. And again, we'll talk more about osmosis and stuff later and pH and stuff like that, but it's really important that we recognize that the number of molecules is going to be really important. So this is actually twice as concentrated. Even though, again, right, even though they do have the same percent by mass because you tossed in 34 grams of each of them, however, the actual number of moles, the actual number of molecules is different. There's twice as much of this ammonia, this NH3, as there is of the phosphine, the pH3. And so how do we take care of this? How do we acknowledge the fact that one has more moles of a substance than the other one? This is why we have molarity. Molarity is going to be a measure of how many moles of stuff are dissolved in a solution. So let's talk about molarity more. Right, so I've got molarity. Molarity has the abbreviation of a capital M, right? It's not a little m. Remember that little m is milli, a little m is meter, but a capital M is molarity. That's the abbreviation for molarity. And molarity is defined as the moles of a solute divided by 1 liter of the solution. Now, if you remember that the percentages, it was per 100 milliliters, but for molarity, it's per 1 liter, 1 full liter of solution. And again, we're going to have some more context with this later. This video is just to kind of introduce the idea of molarity. But this is, again, molarity is going to be really important when we talk about osmosis, when you talk about diffusion, when you talk about things like pH, when you start doing math with the reactions. The molarity is going to be the way that we measure concentrations. And so what I'm going to do in this video is I'm going to show you kind of two main ways that you're going to see molarity problems take shape here. One is going to be just find the molarity. Just what is the molarity of a solution? Just find the molarity. And then the second one will be recognizing that you need to use molarity as a conversion factor, right? You got to use molarity as a conversion factor because if you look at molarity, it's moles per liter. Since it has more than one unit, it's a conversion factor, not an amount. So I'll show you kind of two examples of each of these in this video. There will be a little out of context. We'll see more context in future lessons. So let me show you this very, very first one. Right, so a 4-liter solution contains 10.0 moles of aspirin. What's the molarity of this solution? So this is definitely a find the molarity type question, right? Because it flat out says, what is the molarity? What is the molarity? Now, whenever you're being asked to find the molarity, all you need to do is just remember, okay, molarity. I know that molarity is moles of solute over 1 liter of solution. Over a liter of solution. So that means then that I've got kind of two jobs here. I need to do two things. I need to find how many moles of the solute there are. And I need to find how many liters, right? So I'm basically asking two questions. And then I just put one over the other and solve. This is the most pared down type of question I could possibly give you, right? Because it flat out gives you moles of solute. It says that there are 10 moles of aspirin right there. So I don't have to do any conversions or anything. I just got to transfer this down here and be like, oh, apparently there's 10.0 moles of aspirin in this question. Similarly, again, you don't have to do too much thinking here because if I'm looking for how many liters of solution are we talking about, it flat out says that there are 4 liters. So I just put 4.0 liters down right there. And that's all you really have to do for this question. I found the moles, it flat out told me. I found the liters, it flat out told me. And then you divide one by the other to get 2.5 moles per liter, or in other words, 2.5 molar with a big M. I don't really mind if you use MOL divided by L as your units, moles per liter, or if you put a capital M to show moles per liter. Either way, it means the same thing. And then again, the way that we say this is we'd call this a 2.5 molar solution. So when we say molarity, we say that solution is like, 9.2 molar or 0.001 molar or whatever it is. So that's all we have to do to find the molarity. Now, of course, not all problems are going to be this simple. You're not going to see ones that just give you flat out liters and flat out moles. They might have grams and milliliters, for example. So let me show you one of those types of questions. So again, right, this is a what is the molarity question because it flat out says what is the molarity. So I'm going to do the same sort of thing here. I'm going to remind myself that I know what molarity is. I know that molarity is moles of the solute over liters of solution. And so that means I know I need to find two different things, right? I need to figure out how many moles do we have, and I need to figure out how many liters do we have. But in this one, right, I don't have moles here. They give me grams. I have grams of something, which is not moles, but I do know how to convert grams into moles as long as I know what this compound is, so sodium sulfate. If I remember back to what I know about sulfate, that is SO4 minus 2, then I'll remember that sodium sulfate must be Na2SO4. And in order to convert grams to moles, right, I need a molar mass. If you don't remember what a molar mass is, it's just adding up all of the atomic masses of your compound. So if I have Na2SO4, what we're saying, let me draw that a little lower, that doesn't look like a subscript. Na2SO4, what we're saying is that I've got 2 sodiums, which weigh, I'm just using a periodic table that has 2 sig figs. So that's saying that weighs 2.99, 2 places past the decimal, not 2 sig figs. 1 sulfur, which weighs 32.06, and 4 oxygens, which weigh 16.00. So I just add all that up, and if you add all of those things up, you'll see that you get 142.04 grams per mole. That would be my molar mass of sodium sulfate here. So if I know the molar mass of sodium sulfate, I can convert that grams into moles. So it looks like I've got 37.119 grams of sodium sulfate. If I want to turn that into moles, apparently there's 142.04 grams per mole. And if I calculate that out, right, I'm basically just doing 37 divided by 119. So I've got 37.119 divided by 142.04 gives us 0.261327 and some more. If I look at this, it looks like I've got 5 sig figs and 5 sig figs, so I need to report 5 sig figs, which for us is 0.26133 moles, right? So there's my 5 sig figs, 0.26133 moles. So I figured out how many moles of solute I've got. If any of this seems kind of a little shaky to you, or you're like, wait, what is going on? Go back and watch my videos on molar masses and using the periodic table and everything. But this is just skills that in theory you have already done. You have done this before. And as far as figuring out how many liters of solution, I wasn't given liters, but I was given 250.0 milliliters. And I know how to convert milliliters into liters, right? I know that there's 1,000 milliliters per liter. So that means I have 0.2500 liters, right? So that 25.0 milliliters is 0.2500 liters, so 0.2500 liters. And again, you just divide those by each other to find your molarity. And in this case, my molarity would be 1.045. I can only have 4 sig figs because there's only 4 in that number, molar. So 1.045 molar, or again, you could write 1.045 moles per liter. Either way you want to do it, but they mean the same thing. That big M means moles per liter. And so you'll see different iterations of that, right? You just got to remember that for molarity, you got to find how many moles of solute, how many liters of solution. That's how you're going to calculate your molarity. Now, like I just said, that big M means moles per liter, so that's what we need to use in the other type of molarity question, namely when you're given a molarity and you have to use that molarity as a conversion. So like in this one, right, you're flat out given the molarity. You're shown what the molarity is, in this case, 0.5002 molar. And right, the big key here is to remember that you want to translate this. That big M is moles per liter, so you want to be reading this as 0.5002 moles per liter. You want to be reading that as a conversion factor because that's what we're going to use it as a conversion factor. And so since this is just a conversion factor problem, I'll set it up like I do all of my conversion factor problems, where I'm asking myself, what's my known amount, what's my unknown amount, and what conversions might I need, what conversion factors. Right, so let's get my my knowns down. So it looks like my known here, here's the only thing that's an amount, is 0.850 moles. 0.850 moles. Right, this 0.5002 molar is not an amount because really it has 2 different units in it, right? Really it's moles and liters. Remember, multiple units, probably a conversion factor. The unknown amount that I'm looking for is milliliters, right? It's asking for milliliters, so mLs. And then conversion factors, what conversion factors might I need? I just mentioned I have the molarity thing going on, so 0.5002 moles per liter, right? I just got that from the molarity given in the problem. And I see that I have liters, but I need to get to milliliters, so I'm also going to remember that I have 1,000 milliliters per liter and see if I need to use that also. And so with that, let's see where we can get. Maybe I do need to know that hydrochloric acid is about 36 and a half moles or grams per mole. But let's see if I need the molar mass of hydrochloric acid or not. So if I put this all together, 0.850 moles, my starting amount. Put in my first conversion factor. I have moles in this conversion factor, so I'll use the molarity first. I need to flip it, right, because I need moles on the bottom so they cancel out. So this will be 0.5002 moles per liter. And now I have liters that I need to get rid of, and so there's my liters. So I'll leave that one as it is. Right, so I'll leave liters on the bottom, put 1,000 milliliters on top. And if I solve for that, what I end up getting is 1,699 milliliters. And if I remember that I only have 1, 2, 3 sig figs, then this ends up being 1,700 milliliters, or in other words, 1.70 times 10 to the third milliliters, right? To show that I have 3 sig figs and that one means 1,000, then I have 700. So that's all you'd have to do to figure out the molarity stuff, right? You just set it up, you use it as a conversion factor, you do a normal conversion factor type problem. That's all you really need to do. I'm going to show you one more example, and then I'll let you be on your way. So same sort of thing, I'd recommend pausing right now, give this a crack. It's exactly like the problem that we just did together. Right, the big trick with this is remembering that your 1.5, right, is really 1.5 moles per liter, that's a conversion factor. That's the big key here. So I can go ahead and I'll write my known amounts, my unknown, conversion factors. Same exercise, so my known amount in this case is 500 milliliters, right? That's an amount. So I've got 500.0 milliliters. My unknown amount, it's asking how many grams of glucose. So I need grams of glucose. And then I need some conversion factors. I already know that I've got my molarity, so I'm almost certainly going to have to use molarity. So there's my molarity. It's talking about milliliters, but molarity is in liters, so I'm probably going to need 1,000 milliliters per liter. And I end up in grams, but all this business is about moles, so I'm probably going to need something converting grams into moles. And if you don't know what glucose is C6H12O6. So I just add up all of those, right? 6 carbons, 12 hydrogens, 6 oxygens. I'd add up all those, and you'd find that it comes out to be about 180.156 grams per mole. So I'll use that molar mass. I need a little more space. So 180.156 grams per mole. And I think I've got everything that I need. And again, I'll just check because I'll start. And if I don't get to the unit I want, if I don't get to grams, then I know I need something more. So we'll start with our 500.0 milliliters. I'm in milliliters, so I'll use the one with milliliters. I'll flip this so that the milliliters cancel out. Now I'm in liters, so I'll use my molarity. I'm going to leave that as it is, again, so that the liters cancel. Now I'm in moles, so I want to use my molar mass. I'm going to leave that one alone so that the mole on the bottom cancels. So 1 mole is 180.156 grams. That's going to give me a number in grams. And then, so if you multiply that out, right, 500 times 1 times 1.5 times 180.156 divided by 1,000, you should end up getting about 135.117 grams. But according to my my significant figures for this problem, I've got 1, 2, 3, 4. I only got 1, 2 in that one, and I've got more than that. So I can only use 2 sig figs for this one. So again, that gives me kind of a funny number of 140, or in other words, 1.4 times 10 to the 2 grams. So how many grams would I need if I wanted to make a 1.5 molar solution? I want to make a half liter of it. I would need to add about 140 grams of glucose is the idea. So that's how we would approach these problems. That's how we would use glucose in a question like this. In glucose. That's how we would use molarity in a question like this. And like I said, in the future videos, we'll use molarity in a little bit more context when we talk about osmosis specifically, or with reactions, or like I said, pH or something like that. So if you have any questions or comments, please leave them down below. Highly recommend that you do a ton of practice with this. I posted so much material on our website. So please do like all the practice you possibly can so you feel very, very comfortable with it. It's not hard math. It's just kind of mentally weird for us to do conversion factors with things we are not intuitively familiar with. So now that we're saying moles, people seem to kind of freak out. But if you do a lot of practice, you'll see how routine and monotonous this gets. So study up. Good luck.